And thanks to the organizers for putting on this high-powered program. Yesterday was great, and I'm looking forward to the talks and discussions through the week. So as Rafaela said, I've been tasked with discussing a little bit about what we've been learning about the properties of early star-forming galaxies with JWST. I want to get started with what JWST is telling us about UV slopes and dust at very high redshift, building a little bit on what we heard in Kevin Hainline's talk yesterday. Okay, dust, of course, plays an important role in regulating the bright end of the UV luminosity function. And by measuring UV continuum slopes in these galaxies we're discovering at these very high redshifts with JWST, we have a path towards estimating the typical attenuation levels in the UV emitting component of galaxies out to the highest redshifts that we're seeing. Okay, now what UV slopes do we expect to find? A little refresher here. We look at the UV slopes, the intrinsic UV slopes, versus the stellar population age. These dashed lines shown here show the UV slopes of the intrinsic stellar population for different metallicities. Different colors show different metallicities. And you'll see that the intrinsic stellar population can produce a UV slope of -3, even down to -3.2. Okay, but we're not just observing stellar continuum, we're observing the combination of stellar and nebular continuum, and when you add in the two photon and free bound continuum, you read in these UV slopes. So these solid lines show the combined stellar and nebular UV slopes, and you see that these intrinsic continua with no dust attenuation have values of about -2.6 or -2.5. Okay, so if we go out to JWST and observe UV slopes that are redder than -2.5, this may point to some modest attenuation in these galaxies. Now, Hubble was actually pretty good at measuring UV continuum slopes. Okay, so the consensus from about a decade's worth of work with Hubble is that at redshift 7, UV slopes were pretty blue, ranging between -2 and -2.5 or so. But this was really hard work at redshifts above 9, right? We didn't really know of many galaxies. We didn't have enough filters to properly measure the UV slopes. So sort of the state of the art prior to JWST was in this paper here, where we were able to get UV slopes for about 6 galaxies. Okay, and you can see that the values here on average were about a UV slope of 2. Okay, so this is redder than those intrinsic slopes. So the pre-JWST view here was that there was some modest attenuation already present at redshift 9. Okay, step forward into the modern era with JWST, with NIRCam, we're able to get UV slope measurements now for extremely large samples. Okay, so if you look at redshift 9, we now have over 200 objects that we can make these measurements in, not just the 6 that we could do with Hubble. And of course, we can step out now to redshift 12 to 15 and make the first measurements of the UV continuum slopes at these redshifts too. Okay, so let me just show you what we're finding. At redshift 6 to 8, okay, we see a range of UV colors in galaxies. Some quite blue, as you see on the left over here, with UV slopes of -2.5, -2.6. But as we look at the right-hand part of this figure, we see quite a few objects actually at these redshifts are fairly red. Okay, UV slopes of -1.4. Okay, so these may face significant attenuation. But as we go out to redshifts above 9, okay, looking in the bottom half of this figure here, we see that these red objects begin to disappear and the bulk of the population appears fairly blue. Okay, we can zero in on this redshift evolution more clearly in this figure here. So here we're looking at UV slope versus absolute magnitude, and we see redshift 6 and redshift 7 shown in the two colors. Okay, we see a relationship between UV slope and absolute magnitude, with the brighter objects, the more luminous objects, being a little bit redder. Okay, and again, little redshift evolution between redshift 6 to 8, consistent with what was found with Hubble. But as we go to redshift 9, we start to see some evolution at the bright end of the UV luminosity function. The most luminous objects start to appear blue. Okay, and as we step out yet further to redshift 12 to 15, we see even bluer values. Okay, so the galaxies, these 20 or so objects that we're seeing photometrically at redshift 12 to 15, have typical UV slopes of about minus 2.5. Okay, and we see a similar picture in other studies. Okay, there have been a variety of different groups putting out measurements in different surveys and combinations of different surveys, and the picture appears broadly consistent, right? The typical values at redshifts above 9, above 10, UV slopes are minus 2.5. Now remember, that is exactly the value that an intrinsic stellar population with nebular continuum produces. Okay, so this is consistent with there being almost negligible attenuation in these objects at redshifts 9 to 15 or so. Okay, so there have been many papers discussing what this might imply. I'll just briefly touch on two that we've heard a lot of that have appeared in the literature over the last year or so. Okay, one is that we've heard from Andrea a lot, right, that dust is present, but it has been ejected by radiation pressure in these objects or is offset from the UV emitting regions. Okay, so this might explain how some of these objects, quite luminous, maybe quite massive, appear fairly blue. Okay, another paper that Deshika Narayanan posted on the archive last night suggests that the dust to stellar mass ratios, okay, at these very high redshifts, at redshifts above 10, are much lower, okay, than those even at redshift 7. Okay, and they only start to rise as the stellar masses and star formation rates of galaxies grow. Okay, so you can read Deshika's paper to understand the physics there, but even in relatively massive objects, this paper suggests that the dust to stellar mass ratios aren't going to be high enough to present much attenuation. Okay, now, as we heard yesterday in Kevin's talk, even bluer UV slopes are now discovered at redshift 10. It's pretty striking that in the first handful of spectroscopically confirmed galaxies that we've been able to achieve with JWST, 3 of them show UV slopes between minus 2.8 and minus 3. Okay, you can see these here. We see similar extremely blue systems photometrically, okay, at redshifts above 7. And of course, you'll note that these values, UV slopes approaching minus 3, are bluer than the intrinsic nebular and stellar continuum. Okay, so how do we explain such blue UV slopes, and what might this be telling us about these redshift of greater than 10 objects? Okay, so to reach UV slopes of minus 2.8 to minus 3, you need somehow to get rid of at least some of your nebular continuum, right? We need to move from this solid line down to these dashed lines, right? So the nebular continuum must be weakened by some process. There are 2 processes that might do this. One is that ionizing photons are escaping without being reprocessed into the nebular continuum emission, right? Perhaps leaking through channels in these galaxies. Okay, so you'll be seeing more of the direct stellar continuum in this picture. Now, this is observed in the sunburst arc, in the Lyman continuum leaking region of the sunburst arc, where the UV slope is known to be minus 2.8. Okay, so this is seen at lower redshifts in regions that have very high Lyman continuum leaking escape fractions. Okay, but note, in order to really reproduce the very blue UV slopes that are being seen, you really do need extraordinarily large escape fractions, above 50%, to really get rid of enough of this nebular continuum emission to do that. Okay, what's the other option? I promised 2. Okay, the other is that we have bursty star formation histories. Okay, and these galaxies have recently ceased forming stars. Okay, so the O stars are starting to disappear and your nebular emission is going away. But you still have a blue UV continuum from the late O stars and the B stars that remain. Okay, so you'll note here we see in this red dashed line the UV slope of a simple stellar population, a burst of star formation, and you see indeed it's minus 2.6, that intrinsic value, but then after about 7 million years, it starts to bluein, and it gets to about minus 2.8, right? Once more and more of those O stars start to disappear. So it might be that this is indicative of these bursty star formation histories, and we're observing them just as they're exiting or entering this off mode of star formation. Okay, so remember, we're seeing these in 3 of the first spectroscopically confirmed redshift greater than 10 galaxies. I think understanding what these are, what's driving this, is quite important. But we have these 2 different pictures. Okay, both perhaps a side effect of strong bursts of star formation, but ultimately we're going to need deeper spectroscopy to distinguish which of these is driving the UV slopes to these extremely blue values. Okay, I said a few words about star formation histories and bursty star formation histories. Now I want to tackle this topic more head on. Okay, so what is JWST telling us about the star formation histories and the ionizing photon production efficiencies in these very high redshift systems? Okay, when we look at the properties of these galaxies, do we find indications of the bursty star formation histories that appear able to at least be an important part of explaining the census of galaxies that we're now measuring at redshifts 12 and higher? Okay, so again, this topic got its start over a decade ago with Hubble and Spitzer. When we looked at galaxies at redshifts 7, we saw huge fluxes in Spitzer bandpasses that sampled the rest frame optical emission line. So this suggested that the galaxies at redshift 7 had very large equivalent width oxygen 3 and H beta emission, okay, equivalent widths above 1,000 angstroms. When you see this, this is indicative of a very young stellar population dominating your SED, a young population that was likely formed in a recent burst or upturn of star formation. Okay, so the idea is with Hubble or Spitzer, we were maybe observing galaxies near these peaks of star formation, and when galaxies are in this phase, they are very efficient ionizing agents. They're producing a lot of Lyman continuum radiation relative to the far UV radiation we're seeing at 1,500 angstroms. So before JWST, we started seeing a number of papers suggesting that these early galaxies had very large ionizing photon production efficiencies, and perhaps this might reduce the required escape fractions that you would need to achieve reionization. Of course, with Spitzer, we could only study the bright galaxies, the galaxies at the far bright end of the luminosity function. So it's not at all clear if these are representative. And of course, if star formation histories are bursty, what we were seeing with Spitzer before JWST was just the upturn, the peak, right? We weren't seeing this off mode or this mini quenched phase in between the bursts. Okay, JWST has of course transformed our ability to characterize the spectral energy distributions of early galaxies. And we've seen a lot of great papers looking at these data sets. So with NIRCam, we don't only look at the bright galaxies now, but we can characterize these really faint objects all the way down to minus 17 or so in absolute magnitude. Okay, so we have these SEDs across 6 fields now, thousands of galaxies, and we can ask the question, do all galaxies look like those from Spitzer that I was just showing you, dominated by young populations? Okay, so let's look at the distribution of SEDs we see in these data sets. We do see some objects that show Balmer breaks, okay, providing potential evidence for older populations under the assumption of constant star formation. But indeed, many of these objects show really large equivalent with oxygen 3 and H beta emission, which, as I said, is a characteristic of these young populations. So you'll see these excesses here in these long wavelength NIRCam bands. Note these filters often sample oxygen 3 and H beta and at redshift 6 H alpha. Okay, so you can get photometric measurements of both oxygen 3 and H beta equivalent with and H alpha, which do agree with those from spectroscopy, at least at redshift 6. Okay, so strong oxygen 3 and H beta is common even among faint galaxies. For those of you who followed the exciting work coming out of the NIRCam GRISM, a similar picture is seen there. We see a lot of strong oxygen-3 line emitters. Okay, so what this is telling us is, just like we saw with Spitzer, SEDs with these large equivalent widths are common, right? We're seeing a lot of the galaxies, both bright and faint, are dominated by the light of young populations formed in these recent upturns in star formation, where the star formation rates have increased significantly by factors of few in the last 3 to 10 million years. Right? So these kinds of star formation histories must be common in the reionization era. A lot of galaxies have to be in the midst of these bursts of star formation. Okay, but we're also finding a large subset with NIRCam with young continuum SEDs, so no Balmer break, okay, but weak line emission. Okay, so generally we think of when you have a young population, you should be powering large equivalent width lines, but you'll note here that we're not seeing these strong flux excesses here. So in other words, for these objects, the H alpha, the implied H alpha over UV ratios are very low. Right? These are challenging to explain with constant star formation models. You can see these models when you try to fit these data. They want H alpha, their filter that has H alpha in it, to be stronger than what's observed. Okay, so how do we explain these weak emission line young continuum SEDs? Okay, more flexible star formation histories provide much better solutions, right? So here you see a star formation history that can reproduce this data set where we've had a strong burst about 10 million years ago, and then the object has had a recent decline in its star formation rate. Okay, so what that does is it makes the emission lines weaken because the O stars have started to disappear. But there's still late O stars and B stars to power this young continuum SED. Right? So these kinds of objects are potentially a signature of this population that went through a burst, say 10 million years ago, but now is in that mini-quenched or star formation rate lull phase. Okay, so we're finding these sources, we think, maybe for the first time. And of course, as many of you have heard, these are starting to be confirmed spectroscopically. Okay, so here we see a few examples. Okay, there's more coming in the literature. And when you get prism continuum spectra of these kinds of objects, you really tighten up the past star formation history. And so you see here, you go from this red photometric curve to this gray binned curve, right? So really confirming that these objects with these weak lines are probably this, they have recently undergone a strong decline in their star formation rate. Okay, so just to sum up the sampling of the kinds of galaxies we're seeing, I think NIRCam is identifying the common presence of extreme emission line galaxies. These are likely in this peak phase of their star formation, but now for the first time we're also finding evidence of objects in this mini-quenched or off-mode phase between the bursts. Okay, we're getting the samples now where I think we're finding evidence of both phases of the bursty star formation in these early galaxy samples. Okay, so with these data sets, we can now try to take the next step and look at the distribution of star formation histories across the luminosity function, right? So most work to date looked just at the bright end of the luminosity function, the bright population, which showed these strong bursts were quite common, the large equivalent width oxygen-3 emission. JWST allows us to investigate whether galaxies at the faint end of the luminosity function are equally weighted to these strong bursts, these large equivalent width line emission, right? So we can measure the equivalent width distribution of oxygen-3 and H beta in these 3 bins across the luminosity function, right? So here is what you see in the bright galaxies, and shown beneath it is what was seen with Spitzer prior to JWST. You see quite strong line emission. These are these strong bursts with typical equivalent widths of 700 angstroms or so. But as we move fainter, to the fainter systems, the more abundant faint population, we see these equivalent widths decrease. Okay? At the faint end of the luminosity function, your typical equivalent width is just 300 angstroms. Okay? That is very different to what we were seeing with Spitzer before JWST. So what is going on? Okay, the median oxygen-3 H beta equivalent width is decreasing by a factor of 2.5 as we go down the luminosity function, with these weak line-emitting galaxies becoming more common. Okay, so what is driving this weakening in oxygen-3 and H beta? We think there are two factors contributing. One is the gas phase metallicity, decreasing as we go to these extremely faint objects on average, okay, such that oxygen-3 is weaker. Okay, that will make oxygen-3 weaker. It's not going to make H-alpha weaker. So to reproduce the weakening of H-alpha, we also need the star formation histories at the faint end of the luminosity function to be different on average than those at the bright end, with a larger fraction in the midst of a recent downturn of star formation. So what we're finding now is that 35% of the objects at an absolute magnitude of -17.5 have been in the midst of a strong recent decline in star formation. Okay, and this is contributing as well to this shift in the oxygen-3 and H beta equivalent widths. Okay, so just to show you pictorially what I think the data are suggesting, the most UV luminous galaxies are luminous because they recently underwent a burst of star formation that has bumped up their UV luminosity. Okay, those at the faint end have a more equal mixture of rising and declining star formation histories. Okay, now this is going to impact the ionizing photon production efficiency, right? So in this picture, the most luminous objects are those that have the large ionizing photon production efficiency, but the star formation histories of the less luminous objects, again, are a mixture of the strong bursts with very efficient ionizing production efficiency. But we also have these objects that aren't producing much ionizing radiation at all. So we have this tail to very low ionizing photon production efficiency really showing up at the faint end. Okay. And just to say, the psi-ion values, when you match them by MUV, are consistent with those in the literature. Okay, so just a quick word on where I think we need to go next with this, right? We have these observationally inferred star formation history trends with absolute magnitude, looking at the fraction of the population in strong star formation rate downturns, rises in star formation rate, strong rises in star formation rate. And what you can try to do is figure out what kinds of bursty star formation histories are able to reproduce these trends. Okay, so the first look at jointly fitting the star formation history trends and the UV luminosity function at redshift 6 suggests you need a large dispersion or scatter in your UV luminosity, with that scatter increasing toward lower masses. Okay, you need that to reproduce the trends that I've just showed you. Okay, and this is broadly consistent with the kinds of bursty star formation histories you see in Fire 2 and Sphinx. So I think this kind of analysis is where this field needs to do moving forward. Okay, but I want to just leave that behind to say a final few words on hard radiation fields and nitrogen enhancement. Okay, so this is a story that starts with GNZ11, which we heard about yesterday and which you all have heard about probably many times before that. Right? So this spectrum shows the presence of hard radiation field, high electron densities, and metal poor gas with elevated nitrogen to oxygen ratios. Right? So this is an abundance pattern that is rarely seen in galaxies, suggesting a distinctly different chemical evolution history or scenario, but it is present in a large subset, the second generation population of globular cluster stars. Right? But of course, GNZ11 is one galaxy, right? So is this spectrum unique? Is this galaxy unique? Can we begin to understand how common this abundance pattern is in the early universe? Whether galaxies perhaps go through a phase in their evolution where they have this abundance pattern, perhaps as they undergo bursts of star formation. And can we understand whether there might be a physical connection between this abundance pattern and the radiation field and the electron density we see in GNZ11. Okay, so a natural place to start is objects that have the same radiation field, the same hard radiation fields that GNZ11 does, and two such of these objects have been known to exist at redshifts above 6 for nearly a decade now, right? These are these two carbon-4 emitters shown here. These are lens low-mass galaxies at redshift 6 and 7. Prior to JWST, it was not clear whether these systems had significant nitrogen enhancements, nor was it clear what ionizing sources were powering the hard radiation fields. Both of these systems have been observed with JWST. We see they are in the midst of extremely strong bursts of star formation. Okay, they're well above the main sequence, dominated by stellar populations of just 1 to a few million years. Okay, and these bursts are happening in extremely compact volumes. Okay, we have a star formation rate of about 60 solar masses per year in just 20 parsecs. Right, so we have an extremely high density of O stars in these systems that has almost never been seen in young star clusters locally, particularly those of the metallicities seen here. Okay, so we may expect stellar collisions to be common in these systems, perhaps building up the upper end of the initial mass function. Okay, just to note briefly, this is not what every reionization era galaxy looks like. It's really only that upper 5% of the equivalent width distribution. Okay, so these are just the systems caught in the strongest bursts, but likely this is a phase that many reionization galaxies go through. Okay, so I'll just show you here, these spectra do appear pretty much identical to GNZ11 in many ways. They have nitrogen detections, elevated nitrogen to oxygen, okay, very strong hard radiation field, okay, but and high electron density, strong feedback, but we don't see clear indications of AGN in these systems, okay? There are other nitrogen emitters, but just the emerging picture is that I don't think GNZ11 is unique. We're starting to understand when this abundance pattern is produced, okay? It appears linked to galaxies with extremely dense populations of massive stars formed in a recent intense burst. This is precisely what you'd expect for globular cluster formation, okay? So I'll just close here.
Thank you. Thank you, Dan. So can someone help with the mics, please? No? Thank you. Someone maybe taking the mic there. Yeah, you can start, Kathy.
Hi. Great talk, great overview. Just going back to the UV slopes, do you have any concern as we march out to higher and higher redshifts about the general selection effects of, you know, by its very nature, we're kind of chasing after the bluest objects because they're the most reliable sources of photometric samples. Anything that's like slightly less blue, you know, could potentially have a viable low redshift interloper solution. So what is the impact of that broadly? What are your thoughts on that folded into the evolution of the UV slopes?
Yeah, it's a good question. This is certainly something that plagued Hubble a lot in the past, where we only had a handful of filters longward of the break. And so there was a lot of work developed over the years to try to simulate the impact of that. I think, you know, certainly as you see at redshift 6 to 8, we are seeing the red end systems. I think we have enough filters longward of the break where we could see this at, if they were there at redshifts of 10. Certainly the medium bands and getting lots of medium bands will also help with that sampling. If we start ever really going out to redshift 15 to 20, then I think we'll be in the regime we're in with Hubble where we're really, you know, sort of maybe in error.
So I give the chance to Rachel first, please.
Okay. All right. Thank you. Wonderful talk. Thank you. I have two questions. One is, what happens to the UV slope if there's an AGN in the galaxy? And the other question is, what are the prospects for constraining the actual time scale of the burst phase and the napping phase or whatever lull phase with current or upcoming observations?
Yeah, so to your first question, I think it depends a lot on the relative contribution of the host and the AGN, right? So in a lot of these LRDs, you're still seeing a fairly blue UV slope. Obviously, there are some where that it continues red-end into the UV. So they can be blue, basically. Yeah, well, it can, if the host is dominating the UV, you still might see a blue component, is what I'm saying. And that's what's seen, I think, in a lot of these LRDs. But you can have some cases where you, if it's completely dominating into the UV, you might see a red-end UV slope. To your second question, yes, we would love to get the time scale. It's, Two things to that. In these models that I just showed you, that is not well constrained. You could try to look just at the SCDs, the past star formation histories, and everything we have so far that's in that off mode, nothing shows a decline longer than 40 million years ago. So we're not seeing anything, for example, anything that's not an LRD that quenched 100 million years ago and then has done nothing. But one problem is that if you have like 0.1 solar masses per year over the last 100 million years, and you had something, yeah, you would just lose the burst, right? So that, I think, is something that we want to get out. We'll certainly be able to get a lot of the sort of how much has been quenched in the last 5 million years versus 20 million years, but seeing those things that have really been off for 100, you'll have that degeneracy of what's been happening in between. But I think that's one of the really important questions we want to think more about.
Okay.
Yeah, thank you for nice talk. So Rachel already asked two of my questions, but let me add one thing. So what about the size or morphology estimation for blue and young galaxy?
Yeah, I mean, for a lot of these things, I have one slide that shows this. They tend to be extremely compact. Okay, so obviously that object I showed at the end was just 20 parsecs, right? That was lensed. So this is the best slide I have for demonstrating how the sort of morphologies change across the luminosity function. At the bright end, we tend to see that objects are comprised of a number of clumps, and you can see that here, right? So these are collections of things that are, say, 150 parsecs in near cam separated by 0.5 to 7 kpc or so. Whereas we go down to the faint end, again, this is at the resolution of near cam, we tend to just see one clump. And of course, work by Seiji and others have shown when you have magnification, even these faint ones break apart.
So depending on the filter band, you see nebula continuum or you see only stellar contribution. Do you see any size difference?
Oh, so, I mean, that's an interesting question. I mean, and you could do that even better with just the emission lines, right? Because those are also from the H2 regions, and those come to dominate a given filter. We looked at this just after JWST in one of the first papers, and we didn't see a significant difference, right? Everything sort of looked young, right? The UV continuum and the nebular emission. I'm sure others have looked in this more recently.
Dan, I just wanted to circle back to sort of where you started with UV slopes again, and you talked about two possible interpretations of the very blue colors, and one, if I sort of encapsulate it, one is that they're bursting up, or anyway, that's a possible interpretation of why they're leaking a lot of alignment continuum, so they don't have the nebular continuum. Or they're lulled, they're bursting down, and there's this sort of brief period where, so in the end, then you talked about bright galaxies and faint galaxies. So can I interpret the final explanations on the slope that the bright ones are mostly in this bursting up phase, and it's mostly due to the leaking Lyman continuum and the lack of nebular continuum, and the fainter ones, you were arguing, are more often in the lulling phase, so that blue color is more likely that lull?
I mean, so just to be clear,
simple?
the faint end, 35% are in the sort of lull phase. So there are still strong bursts at the faint end as well, right? But they're just, at the bright end, we're not seeing those much at all. I mean, that is an interesting way to try to think about these things. I think to some extent we should hear from the simulators with leakage as to sort of the time scales of how quickly you clear out those channels. For example, is it at the peak of the burst, or might it be some million years later when you might actually be entering that downturn? I mean, so I don't know exactly how sort of lined up those things.
I mean, that beta of minus 2.8 in the plot that you showed for the lull, it was, I mean, that was a pretty short duration that it reached that. And so, again, these duty cycle issues always seem to be the thing that
it's a short duration.
I find myself wondering about.
And indeed, I said that last week, but as you know, it's a short duration in log space. Right, so I mean, you're talking about, I tried to make that argument last week in Ascona. I mean, and it was correctly pointed out that we're talking about 10 to 20 million years here, and you are catching things, in those periods. But just to this quick point, right, observationally, you should expect O stars, if it's in that on mode, you should see P Cygni features in the spectra where in the other interpretation, you wouldn't see those P Cygni features. So I think there is an observational probe of which of those are dominating.
Alex?
Hi, Alex G. I'm wondering, so you've very carefully avoided mentioning stellar mass, which I think is good, but so should I be thinking of these luminous things as like just very temporarily very luminous, or are they actually...
At redshifts above 7, I think at redshifts above 7, the things are UV luminous because they're low mass things in a burst phase. As you get down to redshift 6, I think things like the Rebels, Galaxies, and others might be somewhat more massive. But yes.
Thanks.
Chris? Sorry.
No, it's all good.
I was going to ask a different question, but because you've got this up, binaries at these sort of ages as well, could they also lead to even bluer UV slopes at these sort of 10, 20 mega year timescales?
So binaries would, right, so they would add ionizing photons at later times after the SSP. So basically, yeah, that might somewhat shift this or dampen this effect overall. I actually haven't looked exactly with the BPAS model to see, but that's a good point.
Any other? Sorry, Andrei, I couldn't see you. Yes, go ahead.
Dan, very nice talk. I was wondering whether interpretation of systematically decreasing equivalent widths towards fainter luminosities could also be explained by systematically increasing escape fractions.
Yes, yeah, I'm glad you asked that. That's a good point. There's a degeneracy in the interpretation of the weak emission lines, and so you could try to reproduce these things with just F escape and with no off mode. We do see the weak emission lines in objects with UV continuum slopes of -2, some -1.8. And so there, that does look like somewhat reddened UV slopes. And so then you have to try to, explain how you have a reddened UV continuum, but then, so you have some dust and gas along the line of sight, but then you also have sight lines where the leakage is getting out. That's plausible, but that's one thing that we've said might push more into the star formation rate downturn interpretation. But you're absolutely right that the leakage is an interpretation.
So I take the chance to ask the last question.
Yes.
And ask in the meantime Alice to comment. So do you see any redshift evolution? So if you compare, given that now the sample is sufficiently big, if you compare what you find at redshift, let's say 6 to 7, to what you find at redshift 8 to 10 or 9 to 10?
With the optical line.
Yes.
So that's a really good question. I should say, to do the star formation history stuff, you really need O3 and H alpha, and so that with medium bands, and that really limits us to redshift 6. Even to do oxygen 3 and H beta, we'd love to know what it is at redshift 10 and higher, but that's shifted out of NIRCam. So MIRI is going to be really important in getting, some idea of what the oxygen 3 plus H beta equivalent with distribution is at redshifts 10 and higher to figure out whether those things might have stronger equivalent width distributions.
Thank you. So let's thank Dan again.